as we start chapter 31, we're going to finish up a topic from chapter 30, and that's energy in fields. If you remember, when we were talking about capacitors, so for capacitors, as you charge the capacitor, the electric field is in there. Now you put energy into the capacitor, and so that means there's energy stored in the capacitor, and so the only place that the energy can be stored is in the electric field. And so we would say that the energy in the capacitor, energy stored in the capacitor, or we could talk about this as potential energy in the capacitor. So potential energy in the capacitor is 1/2 CV squared. So that was the energy that we have stored in the capacitor. And that energy in the capacitor is, again, it was Q squared over 2C. So this is, you also write that as Q squared over 2C. So you can measure it, you can determine it either by the voltage or the charge that's in there. And from that, by dividing by the volume of the capacitor, we saw that the energy density, so little e, little u, which is the energy density in the electric field, was 1/2 epsilon naught E squared. And so that's the energy density in the electric field. This is the energy that is stored in a capacitor that has a certain voltage on it. And of course, that's writing the same thing in terms of charge. And so this was what we'd already discussed in earlier chapters when we were talking about capacitors. So we did all that stuff before spring break. So now we want to talk about an inductor. And we say, well, what's the energy in the inductor? Well, the energy in the inductor is stored in the magnetic field. And so we want to figure out, well, how much energy do we actually have in the inductor? And so if we want to figure out the energy in the inductor, we have to look at the case here of charging an inductor. So if we have an RL circuit, and so we have, this is some initial EMF right here, we have the inductance we have here. So as the current is flowing here, then we're putting energy into the inductor. And so Kirchhoff rule here, this minus L di dt minus IR equals 0. Okay, so if we multiply, if we move things to the other side of the equation, this is going to be equals to L di dt plus IR. So multiply both sides of the equation by I. So this is I squared right there. Okay, and so obviously what we have here is this I times V, and again, this is our V right there. This is our V. So the EMF is the V. That's power. Okay, so this is the power dissipated in the resistor. So this is the power dissipated. So that has to be the power being stored. So this is the total power provided right here, I times V. That's the total power provided by our power supply. And so that means that this term right here is the power being stored. Well, power is rate of change of the energy. So it's the rate of change of the energy. So the rate of change is L I di dt. If the rate of change du dt is equal to L I di dt, if I want to find the amount that's actually stored, I just take the integral of both sides. And so since the inductance is constant, this is the integral of I di dt. Well, we can divide both sides by dt, and so we have integral du equals L integral I di. And so So this is going to be U, that's the energy stored, 1/2 L I squared. And so that is the energy that's stored in the inductor. So now we have a measure of the energy stored in the inductor. And so we compare that to the energy stored in the capacitor. So this is the energy stored in the inductor. So the energy stored in the capacitor, if you remember, it was 1/2 CV squared. And so we have an analogous sort of thing. The energy stored in the inductor when current is flowing. When there's no current flowing, there's no energy in the inductor. Okay. Well, if the energy stored in there is equal to 1/2 Li squared, we know the energy density, little u, is that over the volume. So we think, well, what would be volume here? Well, if we think of the inductor in its simplest form, it's like a solenoid, it's a coil. And so that means the magnetic field in here is constant throughout there. A different shape inductor could possibly exist, but then you don't have constant field, which makes the calculations much more complicated. So we're going to assume a cylindrical inductor, so it's basically a solenoid. And so the volume is going to be basically the area times the length of it. Okay. And so that would mean that the energy density is going to be 1/2 Li squared divided by A times L. Or we can rewrite this as 1/2 L over L I squared over A. Well, if you look back in the book, when we were discussing things such as inductance, we know that L, okay, is going to be N phi over I, where phi is the flux, so that's going to be NBA over I. And so the inductance, okay, because it's a solenoid, then we know that that's going to be equal to, the NBA is going to be mu naught N squared A over L. Okay, and so we look at that and say, well, L over L is going to be equal to mu naught N squared A. Okay, and so this will be U equals 1/2 mu naught N squared A I squared over A. So the A's cancel. Okay, and so we would then be able to say that the energy density is 1/2 mu naught N squared I squared. Okay. But we know that mu naught in I is B in a solenoid. And so if we plug that in up here, that would give us that the energy density in the magnetic field is B squared over 2 mu naught. Okay, with a little bit of algebra. And so that gives us the energy density of in a magnetic field, the energy density. Compare that to the energy density of an electric field, which we derived in an earlier chapter, 1/2 epsilon naught E squared. And so again, we have these constants, epsilon naught and mu naught, the permittivity and permeability of free space, and then we have a 2 in there, also a constant, and then we have the field strengths squared. And so that gives us a measure of the energy density in fields. Anytime you have electric or magnetic fields, you have energy stored in them. And this gives you an idea as to the density of that. The fields are in three-dimensional space. They're always in three-dimensional space. You cannot have a one-dimensional field or two-dimensional field, there are always three dimensions in space, in volume, and so this would give you the energy density stored in that volume space. And that turns out to be a very interesting sort of thing, because what we find is at exceedingly high field strengths such as you have in the presence of a neutron star, or extreme conditions, perhaps near a charged black hole or something, then the energy density of space would exceed potentially the energy density of particles. In which case, you don't get separate particles, or you can create particles out of the field energy. Through E equals mc squared. And so, but that's really the subject of another course.